Yeah, it is a bit of a jumble of wires, but I think it's kind of the register transfer machine is kind of proving its worth at the moment because I'm learning a lot about how this thing works. So just a very brief recap on what I have done so far, and I'm going to point to it with a biro. I've got inputs coming in here, so it's an 8-bit number coming in here, so we'll put a number like what is that number? Let me check. 240. So I've got number 240 coming in binary on here. So that's what that number is there. It comes into my register transfer machine, passes across the data bus of the register transfer machine. There's a buffer here, which is controlled by this switch. So when I press the switch, it allows the binary number onto the bus, and the other end of the bus is connected up by these brightly coloured wires and goes through to my 8-bit binary to decimal display, so you can see the number. So we've got 240 in binary, it passes through the register transfer machine, and we can see the number displayed on the end there. And I've got, well, we've got register 1, register 2, register 3, and register 4. And I'm only going to be interested in 1, 2, and 3 in this little bit that we're doing here. So registers 1 and 2 are ordinary registers connected up to the bus. So if we publish the number 240, I've got these switches here which are set. So this is storing in register 1, that's storing in register 2, that's storing in register 3. So we can transfer the number 240 from the keyboard to register 1. So that's what I've done, and you get a 240 stored in there. And the way it works is you hold down the publish button and then you press the store button of the corresponding register. You only have to press it for a short amount of time, and then you can release the publish. So the publish is level operated, so you take the level low for that, and the store is edge triggered. It goes on the rising edge of the clock pulse. So you just need a very short length or any length of clock pulse to store the value into the register. So what I've done then, I've stored 240 in register 1 and register 2, but let's put a more interesting number, 170, which is on off, on off, on off, on off. Publish that onto the bus and store that in register 2. So now we've got 240 in register 1, 170 in register 2. That's not super clear. I'll see if I can make that a little bit clearer. Okay, what I've done, I've adjusted the lighting a little bit, so hopefully that's a little bit clearer. So now I've got a value of 240 in register 1 and 170 in register 2. But it's not really the value of them that's of interest here, because we're going to put them through a Nand gate. So I've got these two chips here are 74HC00s, which is at 4-bit or 4 quad Nand gates. So two of them combined makes an 8-bit Nand gate. So what's going to happen is that each of the bits in here, so the bit 7 of these two are going to be Nanded together and put into register 3. Bit 6 and bit 6 are going to be Nanded together and put in bit 6 of register 3, all the way along, and to bit 0 of this value and bit 0 of this value are going to be Nanded together and put in here. So let's just do that. So you don't need to publish to do that, you just store, and that's the Nand result. And the reason you don't need to publish is because there is a secret behind the scenes extra bus that goes on here. So register 3 isn't connected to the bus in the normal way, it's only connected as an output, it's not connected as an input. Its inputs come from a little hidden bus that goes from the ALU to the register. So we can just store the value from the output of the ALU into register 3. Nand isn't the most obvious thing. It's a bit counterintuitive, but basically what happens in Nand is if there's a 1 in somewhere in one of the bits and there's a 1 in the other bit, the corresponding bit in the other input, so you've got 2 inputs and 1 output, there's a 1 and there's a 1, then you get a 0. If there's a 1 and a 0, or a 0 and a 1, or a 0 and a 0, then you get a 1. So you only get a 0 if the bits are both 1s. All the rest of the time you get a 1. So we get a 1 here because that one there is 0 and that one there is a 0, we get a 0 here because that one there and that one there are 1s. So Nand isn't, although Nand is the universal gate, it's not exactly the most easy to understand gate. Let's just put it that way. But there is one quite interesting thing about Nand. If you connect the same input to both inputs of a NAND gate, you just invert all the bits in the output. So if I publish register 3 onto the bus, so there's a value of 95, store it in register 1, so we transferred it into register 1, and transfer it into register 2. And now NAND those results, so we NAND register 1 with register 2, they're both the same, we'll get all the bits flipped over, because that's the way that NAND works if you connect both of its inputs together. So there we go, we get the answer inverted. So what I was thinking is, how does this actually transfer into something like a program that a computer would run? And the only program that I could think of that was in any way interesting that you can run on a system as simple as this one is a program to decide whether a number that you give to it is odd or even. So the purpose of this program is that we will put in a number, let's say 15. So there's 15, publish that on the display, there's 15. We want to get out as a result the number, well, an answer to tell us if the number we've put in is odd or even. So if it's odd, I want to get out a 1 on the display, and if it's even, I want to get out a 0, let's say. So how are we going to do this? Well, we can use NAND to do this, because actually if you AND a number with 1, then you get out the result we want. We get out either a 0 or a 1 to say whether it's odd or even. But we've got a NAND gate, so we're going to have to NAND it and then NOT it. So let's just try and write down the sequence of instructions which would get us what we want. So we'd take the input from the keyboard, we'd publish it, and we would store that in register 1. So we're going to use a notation called register transfer language, where you just write down simply in goes to register 1, and that sort of notation is shorthand for publish the input and store it in register 1. So we've got the input is in register 1. Well, now we need a value of 1, which we're going to use in our NAND calculation. So we'll get 1, we'll publish that, and we'll store it in register 2. So that's the literal value of 1 published and stored in register 2. So that's the second instruction. So the third instruction is to take the sum of the result of the ALU and store it in register 3. So we'll NAND those two values together. So I'm expecting, where there's a 1 and a 1, I'm expecting a 0. Where there's anything else, I'm expecting a 1. So let's publish that across like that. So you can see that last bit has changed there. So that is the ALU result to register 3. Now we'll take the ALU result and we'll move it back into register 1. So we'll publish the result, is 254. We'll publish that into register 1. We'll also publish the result of the ALU and put it into register 2. And then we will do the ALU result through the NAND gate into register 3. So now we've got our result that we want, 1, which is what we'd be expecting because the number I put in was 15, which is an odd number. And we will publish register 3 and get the result over on the screen. So that's told us that 15 is an odd number. So we've sort of written in embryonic format there a very, very simple computer program. Let's see if our program works again. Let's put in the number 16 this time, which is obviously that's an even number. Let's check. That's 16, isn't it? Yep, we got 16. So we'll clear out as much as we can. There we go. Back to the start. So we'll follow our instructions again. So we take the input, put it in register 1. We take the literal value of 1, which I write as #1 to denote that it's a literal value. We publish that and store it in register 2. We then get the ALU result into register 3. We then, so actually none of these things, none of the two values have a high value or a 1 in the same position, so we get all 1s on here. So now following on, we publish register 3, which is 255, store it in register 1. I didn't press that for long enough. Store it in register 1. We also publish register 3 and store it in register 2. What's next on our little list of instructions? We take that through to the ALU result, and we then publish the ALU result to the screen. Well, it's a 0 value, so 16 is an even number. So this is like a very, very simple program, but it's a program that I've just performed manually, but I could give those sequence of instructions to anybody who understood this thing, and they could press those buttons and they could get the same result. So I could say to them, put in 170, that's 170, isn't it? Yep, put in 170, stick it in register 1, put a value of 1 into register 2, stick that in register 2, they would do that. Join the two results together with Nand, publish those and put them back into registers 1 and 2, Nand the result of that and publish your result. So 170 that I put in is an even number. So anyone can follow those instructions, but it's pretty tedious and works really slowly. And that is why I need to create a controller section for this project. So the next stage of the project is to design a controller that does all this pressing of buttons automatically and a lot faster than me.